How are we doing? Doing all right? Ready for the weekend? Ready for the end of the semester? Oh, I'm so sorry. What questions do you have? Yes. I do have the quizzes. Is that what you're going to ask me? Yes, I do. I put them in my folder. I remember to put them in there on Wednesday. So, yes, I do have them. Thank you. Sorry, didn't mean to do that. I thought there was a second one stuck on the bottom. Cool. All right. Other questions at all? Okay, so let's finish up talking about graphing polar curves today. So this one we have, it's asking us to graph r equals 1 minus 2 cosine of theta. So the idea behind what we talked about right at the towards the end of class last time was, pardon me, graph the given function that you have in Cartesian coordinates, treating your theta as the x and the r as the y, and then use that information from the Cartesian graph to help us get a graph down in polar. All right, so let's think about some of the transformations that's done to cosine based on this. So if we start with a base graph of cosine, what does the 2 do out in front? What does it change? That changes the amplitude, right? So instead of going from -1 to 1, it goes from -2 to 2. What does the negative sign do? You're going to flip it upside down. Good. And then the 1 out in front will do what? What's the 1 out in front do? Yeah, the vertical shift up 1, right? So instead of going from -2 to 2, it'll go from -1 to 3, right? Because everything's going to get shifted up. And instead of being up, down, and up, it'll be down, up, and down this way, right? So we'll be down at -1 down here at 0. It'll be at 1 at pi over 2. It'll be at 3 at pi. Back at 1 at 3 pi over 2. Back at 0 at 2 pi. And then likewise this way. And sketch it around. I get much better graphs when I actually have graph paper to graph on rather than trying to freehand it on the board. Not great graphs, but better. All right, so that's what the Cartesian graph looks like, right? All right. Remember also what I mentioned last time, that every time that you see this graph dip below the x-axis on the Cartesian graph, or likewise go up and down again. In particular, anytime that you've got x-intercepts here, those are going to close off a loop in polar, right? We're going to make a little loop here. This closes off a loop this way. This closes off a loop this way, and so on down the line. So what might help is figuring out where this graph ends up intersecting the x-axis to help us figure out those guiding lines going into the pole to help us get those loops, right? Okay. So if we set this 1 minus 2 cosine theta equal to 0, solve for cosine of theta, we get cosine theta equals 1/2. So what thetas give you a cosine of 1/2? You get pi over 3, bless you. What else? That was the one that was in quadrant 1. We also get what other quadrant will we be looking in? Yeah, the 5 pi over 3 in quadrant 4, right? Or negative pi over 3, that also works, because I could see them on the graph there, right? Bless you. All right. So what I'm doing with these, again, when I transfer this over to the polar, I want to use those lines, the pi over 3 and the 5 pi over 3, and I'm doing these as dashed lines because they're not part of the graph. But these are going to be guiding lines for my graph as I go into the pole. Okay? That's what I'm using that for. Does that make sense? Okay. So going back up now to our original graph, when theta is 0, the r is -1. Zoom in this way a little bit. Theta was 0, the r is -1, so that means I've got a point right here, don't I? Instead of going to the right one, we would go left one. When when theta is pi over 2, we get +1, so there is a point right here. When theta is pi, we get 3. And when theta was 3 pi over 2, we get 1 again, which is here. And then finally, when theta is 2 pi, I would end up back at that -1 spot again. So those points are corresponding to the high, or I should say the low, middle, high, middle, low points. Just getting some points on there to help me out. No, I don't want to type anything, but thanks, OneNote. It's super helpful. Okay. All right, so as we graph this, we want to think about going around in the circle, right? Start at theta equal to 0, and go around, and hopefully we connect back up at pi over 2. Or pi over 2. 2 pi. Say the right word. All right, so, but in this case, when we're going around, we're starting at this point. That was the theta equal to 0 is here, right? When we start to rotate, we would originally go this way, right? This is we're starting here, we're going to go down. And we still want to rotate in that positive direction as we go, right? So this is we're going to start graphing this. I'm going to get closer and closer to 0, right? Look at my graph. My original graph here is getting closer and closer to 0 as we go, isn't it? So do I want to get closer to the pole or farther away from the pole? If this graph is getting closer and closer to 0, do I want to draw this so I get closer and closer to the pole or farther away? Closer and closer, right? That's how we're going to use that guiding line. This is going to come in this way and follow that guiding line. When we're at pi over 3, which is this line here, my graph is at 0. So that's why I'm using this line to help me go in. So we're drawing it this way, going in closer and closer to the pole, hit the pole, come back out of the pole. Where are we going to go to next? What point are we going to hit next? If I'm going this way and coming in and coming back out, what point am I going to hit next?
I'm going to hit this one. If I'm going this way, I'm going to hit this top point here at pi over 2, right? And notice that makes sense over here from this. As we go from pi over 3 to pi over 2 this way, we're getting farther away from the pole, right? So as I'm spiraling around, I want to get farther from the pole. Where do we go next after that point? To pi, right? So am I going to get closer or farther away as I go? Closer to the pole or farther away from the pole as I go from here to here? It's going to be further, isn't it? Right? Because my R values are getting bigger, aren't they? So as you draw it, you want to make this spiral out farther until I get to pi. Where do we go next? 3 pi over 2. Because we're going from, back on the Cartesian graph again, we're going from here to here, right? Are we getting farther away or closer to the pole as we do that? Closer, right? So we'll go in towards this way, make it smaller. And then I've got to go from this point to this one. But again, I've got to cross through the pole, right? Because if I look back at my graph, as I go from this point to this point, we hit the pole, don't we? And that's why we've got that other guiding line there for us. We're going to come back this way, in through the pole, and then cycle around that way. And so we get this inner loop and outer loop pieces there. What questions do you have on that? It's okay? Yeah? All right. Okay. Let's look at the next one. The next one should look similar to the previous one here. Let's first get a Cartesian graph. Getting that Cartesian graph again, this is a nice review of stuff that we talked about with graph transformations, right? Yeah. Okay. So looking at the sine of theta, what does the sine of theta go between? The theta goes from, the sine goes between -1 and 1, multiplied by 2, it goes between -2 and 2. And then we add 1 to it, what is it going to go between? -1 to 3? Good. All right, so your sine would have started at 0, 0. Instead, it'll start at 1. It'll go up to 3 at pi over 2, back to 1 at pi, -1 at 3 pi over 2, up to 1 at 2 pi. So if I draw this, just like so. Do you see where we might get those kind of the weird inner and outer loops like we did in the previous one? Remember again, every time we cross the axis on a Cartesian graph, we're going to close a loop in the polar graph. Right? So where do you think there might be, just looking at the graph, not asking for the actual values yet, where do you think we might have one of those inner loops? Between what part of the Cartesian graph is telling you that you might have one of those inner loops?
So which point?
Like 3 pi over 2, so like 2 pi.
Oh, from in here?
Yeah.
Yeah, okay. So again, when we're going between those consecutive x-intercepts, that's what closes the loop, right? And notice this one is bigger. That hump is bigger than this one, isn't it? So I'm expecting something that's going to give me a big loop and then a little loop inside of it. Does that make sense? This bigger hump here is giving me a bigger loop. This little hump here is giving me a smaller loop. Both of them have to hit the pole. So I'm expecting a big one and a little one inside of it. You don't look like you believe. Okay.
Do we understand why these x-intercepts are corresponding to closing off a loop? It's okay if the answer is no. Do we understand why those x-intercepts are corresponding to closing off a loop?
You can explain it.
Okay, sure. All right, good.
Okay, so what's the R value at each of these points? Remember, we're graphing this with theta being the x and the R being the y. So what's the R value at each of these points? 0, right? If the R value is 0, you're standing at the pole. Right? R is the distance from the pole. If R is 0, then you're on the pole. Yeah? Okay. These are these the same angle? No, they would have to be exactly 2 pi apart to be the same angle, essentially, right? So since these are not the same angle, you're coming into the pole at different angles. So that's what's closing off the loop. So this one would be coming in at, let me go this way.
This one would be coming in to the pole this way, say, because I'm down there at a negative something or another. This one would be coming into the pole over here somewhere, this way. So that's what's closing off the loop. I'm coming into the pole at different angles. Does that make sense? Okay. Erase that out of there. All right. So again, consecutive intercepts are what's telling you where that loop is closed off. This loop, since it goes higher, since my R value is bigger, right? The highest R value is 3. That loop's going to be bigger than this one because the biggest R value here in absolute value is 1. It's negative, but it's the biggest absolute value is 1. So those points are corresponding to things that are farther from the pole than these are. So that's when we get a big loop and a small loop. All right. So let's plot some points and see what we get. That's the point 0, 1 in Cartesian coordinates. But that corresponds to an R value of 1 and a theta value of 0. So I would plot that right here. Going back up here again, this point, the input's pi over 2, the output's 3. So that's going to correspond to the point 3 comma pi over 2. Going back down here, R value 3, rotate around to pi over 2 is here. Right? Go back up here. When I look at pi, which is right here, notice the R value at pi is 1. So we'll be right here, because that's the angle of pi, right? 3 pi over 2. Scroll back up one more time. 3 pi over 2 is, that point, the R value is negative 1. The R value is negative 1, right? So 3 pi over 2 is usually we think about down here, correct? That way? But since the r value is -1, that point's going to be there, isn't it? And then when we put in 2 pi, we'll get the same thing as when we put in 0. We'll end up back where we started. Yeah? Okay. So, pardon me, sorry. Now when we graph this, notice that we got to this -1. At some point we would have had to go through the pole, right? So those x-intercepts, or those theta-intercepts, if you will, are helpful to get where we're going to go through the pole, to get those guiding lines, right? So the equation that we graphed was 1 plus 2 sine theta equals 0. Or sorry, was 1 plus 2 sine theta. Set that equal to 0. We had sine of theta is -1/2. When is your sine value equal to -1/2? Okay, negative pi over 6 works, good. And where else? A little bit farther than 5 pi over 6, because I'm still in quadrant 2. It's 7 pi over 6, right? Yeah, good. Negative pi over 6 is the same thing as 11 pi over 6, so we're over here. Here's one of our guiding lines is here. And this one would be the other one. Try not to put too much in there to clog up the graph. It's okay? All right. So again, we'll start here. I like to start at 0 for our theta. Start here. I need to get from here to here, right? This was the one we put in for pi over 2 up here, right? Going back up to my graph, that's, again, corresponding to going from here to here. Are the r values getting bigger or smaller? Bigger, right? So as we sweep around, and again, I'm not looking for perfect. I'm just looking for the idea, right? As my theta sweeps, I should get farther from the pole. Doesn't have to be perfect. It's just the idea. You don't have to put extra points in there. Then I have to get from this point to this point. Again, looking back up at my Cartesian graph, that's corresponding to going this way. The r values are getting closer, right? They're getting smaller. So I should make this sweep in. The next point I have to get to is here, but remember this came up by using a -1, right? So at some point I had to go through the pole, and this is where the guiding line is going to come in right here, right? This guiding line is going to help. I'm going to come in, follow that line in, follow that line. No, I was going to follow the line out, but I didn't. Follow that line in, follow the line out to get to here. And then again, I've got to get from this point to this one. But again, this was negative, this was positive. So I have to hit the pole on the way out. I've got my guiding line right here. I have the 11 pi over 6 or the negative pi over 6. So we'll come around this way into there. Let me get that graph. Questions?
Question.
Yeah.
Like on the Cartesian graph and to the like where the negatives are.
Mm-hmm.
To the left side of the y-axis. We have roughly like drop those.
So what the graph just ends up repeating, so it'll just end up tracing over itself over and over again. So usually when you go from 0 to 2 pi, it'll give you the whole graph. Now there'll be weird cases where it wouldn't, but you're not going to have to do one by hand that way. Okay. But notice over here, if you did this side, if you go from negative pi over 2, well, let's do it this way. If I'm over here at negative 2 pi, well, that's the same thing as being at 0. And you would still be increasing around, decreasing down, going through the pole. And it's just going to end up just tracing over itself over and over again. Other questions? Okay. But it was a very good question that you asked, because sometimes you have to worry about other parts of the graph. And this is comes up when you want to use graphing devices instead. Now, we're not going to spend a lot of time on this because I'm more interested in, can you get a graph of the polar graph relatively quickly? But this is helpful if you've got some weird graphs. So just to show you what this first one would look like, let me go over to Desmos real quick. Maybe. If I do r equals sine of theta over 4, notice what this graph looks like. Why do I keep doing that today? Notice that graph looks a little bit strange, doesn't it? Some of these are kind of fun, the graphs that you get from the polar coordinates. The idea here, though, is that if you think about how you would start graphing this, it would start at the origin, because if I put theta in for 0, I only did 0. By the time you get to pi, I'm here. Right? So, well, just follow this around. By the time I get to pi, I'm here. By the time I get to 2 pi, I'm not here. Right? I haven't connected back up again. Why is that? Well, what does this 4 inside do to the period? You have the constant on the inside of the function. What does it do to the period?
Divide it by 4.
It can be divided by 1/4, right? Because we do the opposite on the inside. So really, it's going to have since we're dividing by 4, it really has the effect of multiplying the period by 4, which changes the period from 2 pi to 8 pi. Right? Makes the period bigger. So it's taking it 8 pi to start repeating. So that's why when we're drawing this out, I get from here to there. I'm not done yet. That's only 2 pi. I go around this way to this part to here. I've now done 4 pi. This gives me 6 pi to here, and then finally, if I got this right, I don't know, whatever, doesn't matter. I've lost my track of where I was. But eventually you get back to the pole. It takes a little while, but you eventually get there. So this 4 on the inside changes the period of the sine, how long it's going to take to repeat. And notice that Desmos did this part automatically, by the way. It put in 0 to 8 pi for theta. So if you were going to do this on your graphing calculator, though, it's not going to do it for you automatically. If you do this on a graphing calculator, you have to tell it the smallest theta you want to use and the biggest theta you want to use. The idea behind that is just simply what we know about our functions, the periods of our functions. So we know that this should start repeating when I do multiples of 2 pi added to the inside, right? We know that in general, if I do sine of x plus 2 pi, that's the same thing as sine of x, right? Agree with that? Okay. So thinking over here of what we would need, I want these coterminal angles with theta to match back up with what we started with. So I would need, if I think about just using this idea here, we would want something to be theta plus some multiple of 2 pi to end up back to where we started. Well, we should write it this way. I should write the sine of this to be the same as the sine of theta over 4. Right? This is what we want when we're done. The reason why we need to put in this plus 2 pi k here is because I need to make sure that I'm all the way back around to where I started for a theta, right? If my thetas are not coterminal, then I can't be at the same point. Unless my r's are the opposite of each other, but then the curves will be going in a different direction. I need my thetas to be coterminal, right? We agree? Okay. So that's why I've got the 2 pi k in here. The only way I can possibly get the thetas to match is if they're coterminal. We know we get coterminal angles by adding or subtracting multiples of 2 pi. Right? Now, using this idea up here, the only way these two things can be equal is if this, pardon me, if this part here ends up being a multiple of 2 pi over that part. Right? So we need, what do we need? Oops. We need that 2 pi k over 4 to be a multiple of 2 pi. Not a multiple of pi, but a multiple of 2 pi. Okay, think about why. I'll have theta over 4 plus 2 pi k over 4, if I split that fraction. When I get that, I want it to be the same thing as sine of theta over 4. Well, I need to use this identity, right? I'm trying to get the same answer out. I'm trying to use this identity. This identity also works if I do 2 pi times 2, or 2 pi times 3, or 2 pi times 4. It's just saying the period's 2 pi, right? So I need this extra piece here to be some multiple of 2 pi so I can apply that identity, right? If I'm going to get this to be a multiple of 2 pi, like I said, not just a multiple of pi, but a multiple of 2 pi. It's interesting because I'm not getting 8. I definitely need 8. So I'm done. So I put in 4 for k. Oh, okay. So in order to get this to be a multiple of 2 pi, we certainly need our k to be 4, don't we? That's my problem. I need my k to be 4, don't I? Okay. I should say at least 4. It needs to be a multiple of 4. I'll say it's at least 4. So now if our k is 4, I just got lost in what I needed to explain next. I apologize for that. So we need theta to go from 0 to 0 plus 2 pi times the 4. 0 is where we started. 4 is the value for k that we put in. And then I'm just looking at what we've got in here for our theta to be coterminal. And that's where the 8 pi comes from the highest point that we need. And notice that Desmos, when you use Desmos, it automatically selected it. But of course, if you're doing this on your graphing calculator, it's not going to automatically select it for you. You've got to figure out what to type in. I know I didn't do a good job explaining this. So let's do another one. Okay. Let's look at the 2 plus cosine of theta over 3. 5 theta over 3. So again, we need cosine of 5 times theta plus 2 pi k all over 3 to give me the same thing as cosine of 5 theta over 3. Again, if I'm going to get the same thetas as I'm repeating, the angle has to be coterminal with theta. That's why I've got this 2 pi k in here. Does that make sense? You okay with that part? Why that's in there? Okay. We also need then, if I just compare the two pieces, you'd have 5 theta over 3 plus 10 pi k over 3 equals 5 theta over 3, right? I'm just kidding. It's not really equal. I'm just comparing the two things. I shouldn't write an equal sign because I really am not doing equals. I'm looking at the inputs now for my cosine, right? In order for me to get the same cosine value out, this piece here has to be a multiple of 2 pi. I should say always get the same cosine value out, right? Not just sometimes. In order for me to get the same cosine value out here as I do over here, this piece right here better be a multiple of 2 pi. It better be, right? This piece right here better be a multiple of 2 pi. Otherwise, I'm not going to get the same cosine value out all the time. So what we're trying to do is make this first part here is making sure we get the same theta value out, coterminal theta. The second part is making sure that we really get the same r value, and now I'm the same points on the graph. And it's just retracing its steps. Okay? So I need 10 pi k at 10 pi k over 3 to be a multiple of 2 pi. Well, what better you plug in for k then? What do we need to go away in order for this to be a multiple of 2 pi? What needs to go away? The 3 needs to go away, right? So what better we use for k? 3, yeah. That'll make the... Notice that the 3's will cancel then, and 10 pi is a multiple of 2 pi, isn't it? I should say an integral multiple of 2 pi. Agreed? So for our range then, we'll use theta equals 0 to theta equals 0 plus 2 pi times 3, or 6 pi in this case. Now let's see if that was what Desmos automatically selects for us. Let's go back over here. Now, of course, I've forgotten what the function is. There we go. Oh, wrong one. Cosine of 5 pi over 3. Okay. Ooh. 2 plus cosine of 5 theta. 2 plus cosine of 5 theta over 3. R equals, sorry. And notice that, if you can see it up there, Desmos automatically selected 0 to 6 pi. Okay? We're all very thrilled about it. Again, the time that you would need to be able to do this is if you're trying to use your graphing calculator to get a range for your thetas so that you get a complete graph. Okay? And when you've got these denominators in here that extend your period rather than shrink your period, you can't always just use 0 to 2 pi. Usually, with nicer functions that we've been graphing, 0 to 2 pi is just fine. But when you've got these things that expand your period, you've got to use longer intervals to get a whole graph. That's the idea. Now, of course, if you're doing this in a practical setting, you've got programs like this that automatically select the interval for you, and you don't have to worry about it. But that's really the only reason why we're doing this, is making sure that if we're using a graphing calculator, we can get the interval that we want. And we just want to make sure you can do these, basically the ones on WebAssign, because I'm not going to focus as much on that on the exam anyway. But it is a useful skill for later. Any questions on that at all? I'll leave the last couple there for practice for you. I do want to get into a little bit of new stuff today to get it started to make sure that we get it done on Monday. So last stuff we're going to talk about is how to represent complex numbers using polar coordinates. So remember, your complex numbers come about from trying to do square roots of negative numbers. And so your I, you get the number I that comes out of those. When you do square root of -1, you get I. So one of the things that you can do with complex numbers is represent them graphically. And this is where the polar coordinates part is going to come in. All right, so if you want to represent a complex number in polar form, well, first let's just talk about how we graph them. So complex numbers always have a real part, the part that doesn't have an I, and an imaginary part, the part that does have an I. So we can think of the real part as being basically your x coordinate, and your imaginary part as being the y coordinate. So if I want to plot the polar coordinate, if I want to plot the complex number 1 plus 3i, I go right 1 and up 3. There it is. So again, the real part's your x coordinate. The imaginary part is the y coordinate. Okay. Here, real part is 2. Imaginary part is -2. So we would plot it down here. The next one, Samantha, you have 2 of those. Sorry. So this one, your real part is -2. Whoops. Your imaginary part is 2 times square root of 3. Square root of 3 is a little bit bigger than 1.7. 2 times 1.7 is 3.4, so it's a little bit less than 3.5. Be up there. Last one here, what's the real part on that last one? 0. So you wouldn't go left or right at all. You'd stay on the y-axis, and you would go down -4 units. That's nothing hard, right? Just making sure you know which one's the x and which one's the y. All right, so how does this apply to trigonometry? Well, we already know that if we can represent the points in rectangular coordinates, in Cartesian coordinates, I can also represent them in polar coordinates, right? So that's where we're headed. Remember, one of the pieces of your polar coordinates is how far are you from the pole, right? That's the r value. Well, your r value is the square. Remember, we have the x squared plus y squared equals r squared as one of our conversions. Or you can figure out the r by doing the square root of that, right? We've done that before with converting to polar. This is where the modulus of the complex number comes from. If I have a plus bi, then I can think about this as being my x coordinate and my y coordinate. I can talk about how far that is from the origin. We use absolute value bars to represent the modulus of a complex number because absolute value for a real number is distance from the origin. It's distance from 0. So it's a distance idea. Same thing here. This just corresponds to what the R value you would have in polar. That's how you calculate modulus. So not to do all of them, but if I did the first one, and I want to do the modulus of 1 plus 3i, that would be square root of 1 squared plus 3 squared, which gives me square root of 10. If I did the third one, notice when you do the modulus, you do not put the I with it. Do not put the I with it. Okay. Negative 2 squared is 4. We get 4 times 3 is 12, so we'll get square root of 16. If you simplify that, you'll get 4 for that one. When you square 2 root 3, you get 12. So you get 4 plus 12 there. Again, that's just like finding the R value, right? We agree? Just like finding the R value? These next ones are just playing around with drawing some graphs. If your A value is greater than 1, which points are you talking about on the graph? A, again, represents which coordinate? The X, right? So you're just wanting to shade in the points that have the A value or the X coordinate being greater than 1. So I would shade in this side. Would we include the line x equals 1? Looking at this, do I include or exclude? Exclude it, so we always use that. We use a dash line for that. So really, all this is asking you for is to graph the set of points that have an x coordinate bigger than 1. Graph x is greater than 1, that inequality. Not particularly exciting, but that's what it's asking you to do. Okay? What about the next one? The next one's a little bit more interesting. This says graph, usually if we're talking about a complex number, we use z to represent the complex number. This one wants the complex numbers that have modulus less than 2. Okay. Let's think about it this way. Oops. I want the modulus of a plus bi to be less than 2. Modulus, again, is square root of a squared plus b squared. Oops, not 4. I jumped ahead one step. We want square root of a squared plus b squared to be less than 2. Now let's get rid of the square root, which is what I tried to do before a little bit too early. Let's square both sides. We want a squared plus b squared to be less than 4. Again, a represents the x coordinate. The b represents the y coordinate. If this were an equal sign, what kind of shape would you have if you had x squared plus y squared equals 4? What's it? Let me a line because I got the squares, right?
Oh, it's a problem.